Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथिरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारी एबे मु प्लस 3 CBCS फिजिक्स ऑनर्स जीई आ MSc फिजिक्स ऑनलाइन क्लासेस रो वीडियोस अपलोड करूची। जदि भल लागिला ताले वीडियोस को लाइक कर देबा और चैनल को सब्सक्राइब कर देबो। यू कैन शेयर इट विथ योर फ्रेंड्स आल्सो, इट्स कंप्लीटली फ्री ऑफ कॉस्ट। लेटेस्ट वीडियो नोटिफिकेशन पई बेल आइकन को एठी ऑल रे सेट कर देबो। तापरे वीडियोज रो क्लैरिटी बढ़ावा पई गो टू सेटिंग्स, क्वालिटी, एडवांस उपरे क्लिक करी यू कैन इंक्रीज द रिजोल्यूशन। सबू वीडियोज पई पीडीएफ नोट्स मु पठेबी जोटा एठी ड्रॉप डाउन लिस्ट को क्लिक करी यू कैन गेट द लिंक फ्रॉम द डिस्क्रिप्शन बॉक्स। तापरे मोर चैनल नेम को क्लिक कले सबू वीडियोज को मु यूनिट वाइज एच पार सिलेबस सजाई की रखिथिबी व्हिच यू कैन गेट फ्रॉम द प्लेलिस्ट एठी सर्च करि परिबो। ओके, थैंक यू। हेलो स्टूडेंट्स, आज टॉपिक रे हमें रिजोनेंस जो थरे की ब्रिट-विजनर डिस्पर्शन फार्मूला ए विषय रे पढिबा। सो रिजोनेंस क्रॉस सेक्शन ऑलरेडी या पूर्वरु आमे न्यूक्लियर क्रॉस सेक्शन रे रिएक्शन क्रॉस सेक्शन आउ इलास्टिक क्रॉस सेक्शन विषय रे पढि सरछु। सो ए जो कांसेप्ट क्रॉस सेक्शन रो आ ता सहित लेवल विड्थ रो याको हमें अप्लाई करि परिबा इन द केस ऑफ रिजोनेंसेस इन ए क्वांटिटेटिव मैनर। सो जदि गोटे पार्टिकुलरली इंपोर्टेंट केस आमे नौचु फॉर द केस ऑफ योर रिजोनेंस प्रोसेस गोटे थ्योरेटिकल फार्मूला ए क्रॉस सेक्शन पई डेराइव करथिले ब्रिट आउ विजनर, जी ब्रिट आउ EP विजनर इन द यूनाइटेड स्टेट्स इन द ईयर 1936। सो एटा होची सिंपलेस्ट फॉर्म which will give you the value of the cross section in the neighborhood of a single resonance level which is formed by an incident particle having zero angular momentum, that is zero spin, and also charge zero, so that spin and coulomb effects can be neglected, right? So ebe result kono hela, it will be analogous to the theory of optical dispersion. तेणु करी ए मेन फार्मूला जो आमे पाइबा याको oftenly dispersion formula बोली की मध्य कहा जाए। Okay, so whether or not the level of a compound nucleus is bound, the excitation by an incident particle can be treated as analogous to the excitation of the oscillations which are produced in an electric circuit by the electromagnetic wave. Okay, so wave particle duality kotha bi eti aschi. Now we therefore expect the nuclear cross section to vary with the incident energy in the same way re hi vary karibo as in the case of energy in case of your forced oscillation with respect to the incident frequency. Okay, mane rakho, nuclear cross section with incident energy same as energy in forced oscillation with incident frequency. Now classical resonant circuit jodi ame kahiba, it will absorb the energy because of the resistive levels. So in the nuclear case kono habo, damping will arise. Already tome damping विषय रे जानी छो। ओके, जो थरे की एम्पलीट्यूड धीरे धीरे कमी जाए। So damping will arise because the possibility रहउची एठी decay रो। ओके, nuclear decay possibility पई damping arise करिवो, and because of this possibility the nuclear state has a finite width, that is the level width, which is gamma. Okay, now the wave function of the decaying nuclear state which is having suppose mean energy E0 याको हमें लिखि परिबा as psi RT, which is equal to psi R e to the power minus I E0 t by h cross then of exponential minus gamma t by 2 h cross. एटा मने रखिबो। Okay, so this will correspond to the exponential decrease काहे कि because exponential ले देखो minus factor टा एठी अछि। Okay, so exponential decrease of intensity of excitation, that is mod of psi RT square with respect to time constant or the lifetime tau, which is h cross by gamma, right? Now this wave function also shows that a decaying state is not a state of definite energy E, rather it is of the form psi R e to the power minus I e t h cross by t, and nevertheless it can be represented by superposition of waves which are stationary having slight difference in energy E. Okay, now different amplitude रहिबो, suppose AE as a Fourier integral of the type psi RT integration minus infinity to infinity AE e to the power minus I e t pi h cross de. Now Fourier analysis को एबे हमें apply करिबा, so that we can show that the energy E are grouped about a mean energy that is E0 with a spread of order of gamma equal to h cross lambda. So एबे इक्वेशन जो दुईटा हमें पाइला psi r t रो ताको दुईटा को एबे इक्वेट करिबा, ताले accordingly e to the power minus gamma t by 2h cross or e to the power minus lambda t by 2 becomes equal to this integration, which is the Fourier integral. Now एबे Fourier theory apply करिबा for any well behaved function which is ft. It can be represented as ft equal to 1 by 2 pi limit r tends to infinity. Let us say the limits of the integration is from minus ohm to ohm e to the power minus I omega t d omega, then minus infinity to infinity e to the power I omega t dash ft dash dt dash. Okay, so yes, it is formation of the Fourier theorem for a well behaved function ft. Now applying this function e to the power minus lambda t by 2, we get the amplitude of the state of energy E as AE to be equal to 1 by 2 pi h cross, then limit अछि लागिला 0 to infinity e to the power I e minus e0 divided by h cross minus lambda by 2 एतिकी रहिला factor into t dash then dt dash. Okay, जोटा कि सिंप्लीफाई करले इंटीग्रेशन को यदि हमें काढिबा, its value will be this much. Okay, I by 2 pi 1 by e minus e0 plus I h cross lambda by 2, right? Now here we have assumed that in the case of the decaying system as was prepared at initial time t equal to 0, so the probability of finding the system with a given energy E will be proportional to the amplitude square. So mod a e square आमे ताको बाहर कर देला, हिसाब रे लिखि देला, आसीगला केते 1 by 4 pi square into 1 by e minus e0 square plus gamma square by 4. Okay, एटा डायरेक्ट याको एक्सपेंशन करी कि बाहर करछि. So एति के पाइ सारला परे here you can see a figure जोतरे कि reaction cross section as a function of incident channel energy E0 in the resonance region देखौछि. Okay, so level shape टा एठी फिगर रे हमें देखिबा को पाउछु, which is exactly pure radiative decay. देखो एठी ए हिसाब रे गुटे हला E0 पाई आ गुटे एठी आछि E0 dash पाई. Okay, having a distance which is capital D, right? So ए जो radiative decay रहउछि purely, किंतु को जगह रे रहउनी except that the particle emission is low included by using the total width gamma जोटा level width instead of radiative width gamma of gamma dash. Okay, एठी E0 dash रो state जो level ए जगह रे अछि, E0 टा ए height रे अछि, and this is our ground state, right? So the cross section for excitation of the level by collision of some particle x with the nucleus capital X is therefore expected to have a form like एटी एटा आछि तमरो जो न्यूक्लियर क्रॉस सेक्शन sigma x equal to c by e minus e0 plus gamma square by 4. Okay, जो थिरे कि c होछि गुटे कांस्टेंट. Okay, एठी देखो फिगर रे याकू ये बुझैछि, ए जो क्रॉस सेक्शन टा ई सर्किल रे आछि sigma x, the particle is here small x, this is our nucleus capital X. Okay, एठी v हे गला जो डिस्टेंस कहउछि जदियो एटा होछि वेलोसिटी. Okay, केमति आछि हमें आकू याकू देखिबा, कैपिटल V होछि एठी वॉल्यूम टा, राइट? सो सपोज दैट द कंपाउंड न्यूक्लियस फॉर्मेशन हमें एठी सपोज करूछु. ओके, आवर डीके प्रोसेस टेक्स प्लेस इन अ बॉक्स व्हिच इज हैविंग अ वॉल्यूम कैपिटल V and containing one nucleus that is capital X and one particle that is small x, right? Now if the states are quantized, the number of states of motion of the particles with momentum between p and p plus dp, एटा केते हेबो, एटा तमरो जो फेज स्पेस रो पाउछु यार वैल्यू 4 पाई p स्क्वायर dp into v by h क्यूब हे गला जो गोटे सेल रो वॉल्यूम, राइट? ताले the probability of formation of the compound level per unit time will be equal to how much? The number of possible states of motion into the probability that the nucleus X is contained within the small volume sigma x v. Okay, as I said, small v is here the velocity. Okay, so this small volume sigma xp, which is swept out by the effective collision area per second, that is dp equal to 4 pi p square dp by h cube into v into sigma x v by v. So एठी देखो v आउ v एठी तळे ऊपर कटि जिवो एतिकी आसीगला वैल्यू. Now substituting the value of sigma x from equation 128 जो sigma x रो वैल्यू टा पाइतिला ए इक्वेशन रे पकेबा आ फर्दर इंटीग्रेट कर देले हमें over the energy spectrum we get p, which is coming out as the integration minus infinity to infinity. Okay, एठी हमें sigma x रो वैल्यू पुट कर देला. Okay, याको एबे रिप्लेस कर देला with de. Okay, dp को de हिसाब रे रिप्लेस कर देला. Okay, momentum थिला energy हिसाब रे हमें याको लिखि देला. Right, now if we assume that the variation of the channel wavelength, that is lambda, of the particle over the level width gamma may be neglected, then probability of formation per second एबे याको आउट के सिंपलीफाई कर दबा एबे. So इंटीग्रेशन टा सिंपलीफाई है कि 4 pi c by h lambda square 2 by gamma tan inverse 2 into e minus e0 by gamma जो थरे की लिमिट पड़ुची minus infinity to infinity. So यार अल्टीमेट वैल्यू टा आसीबो c by pi h cross lambda cross square gamma. Okay, so एठी probability of decay per second ही जाउची gamma x by h cross. Okay, so एठी gamma x कोन, it is the partial width of the compound level for the emission of the particle x. Now equilibrium state रे probability of formation per second would be equal to the probability of decay per second of the excited state back into the system, which is the compound nucleus system x plus x. Hence c by pi h cross lambda cross square gamma will be equal to gamma x by h cross, और c रो वैल्यू हमें एतिकी पाई गला pi lambda cross square gamma x gamma. So एई वैल्यू को एबे c रो जो अछि 128 इक्वेशन रे पुट करिबा. So cross section for the formation of the level becomes sigma x e equal to pi lambda cross square gamma x gamma by e minus e0 square plus gamma square by 4. Now for the process x of xy we obtain the reaction cross section, that is sigma r, to be equal to sigma xy of e, which is sigma x gamma y by gamma. So एबे हमें एठी sigma x रो वैल्यू जदी पुट कर देला आ बाकी gamma y by gamma को मल्टीप्लाई कर देले तळे ऊपर gamma कटि जिवो एतिकी बाहरला हमर वैल्यू टा. So it is gamma x और gamma y होची partial level widths, which are defined as gamma x tau x equal to h cross, which is equal to gamma y tau y. So it is tau x tau y kono, these are the mean lifetime that the compound nucleus would have if the elastic scattering of x or the emission of y were the only possible modes of decay. Right, एबे कंसीडर करिबा हमें स्पिन को. जदि स्पिन कंसीडर कर देला ताले ए इक्वेशन रे RHS जो अछि must be multiplied with a factor, that is gc, which is equal to 2ic plus 1 by 2ix plus 1 into 2i capital X plus 1. एठी ix इगला एंगुलर मोमेंटम टोटल टा of the incident particle, I capital X इगला similarly of the target nucleus, IC इगला that of the compound nucleus. Okay, so the g factor asigala, which is formed only by those orbital angular momentum, that is Lx, which satisfy the condition IC equal to Ix plus Ix plus Lx. Okay, and we have the value, this is your pi x into pi x minus 1 Lx equal to pi c. Okay, so it a multiplication factor हिसाब रे गुटे हमें लिखिला. Hence the nuclear cross section in which the particle must have definite spins, then the relation 133 याकू एबे हमें लिखि परिबा रिएक्शन क्रॉस सेक्शन. एबे यार वैल्यू इंक्लूडिंग स्पिन हि जिवो एतिकी हमें केवल वैल्यू टा को पुट कर देला ही जाऊ. Right, so this is known as the Breit-Wigner single resonance level formula, this one. And suppose for the case of neutron and gamma reaction in a particular case, then we have sigma n gamma equal to pi h cross 2 ic bar plus 1 divided by 2 into 2 ix plus 1 gamma n gamma of gamma e minus e0 square gamma square by 4, and this is maximum when e is equal to 0 because a quantity ta 0 ହେଇଯିବ. Okay, ଏଟା reduce କରିଗଲା 4 pi lambda cross square gc gamma n gamma gamma by gamma square. Okay, for the case of e equal to e0 plus or minus gamma by 2, sigma is equal to half of sigma maximum. Okay, sigma maximum रो अधा ହେଇଯିବ. Hence এই जो gamma होची कोन, it is the full width at half maximum. This is very important. Gamma कोन कहबा full width at half maximum, and a sharp resonance correspond to a narrow width gamma, and thus to an excited state of long life. Okay, so a larger possible capture cross section will occur when gamma n is equal to gamma gamma, which is equal to gamma by 2, and its maximum possible value kete hela na sigma maximum, which is pi gc lambda cross square. So the width of the resonance peak affects the cross section, and in a general way jodi peak broad rauchi covering a large energy range, then the cross sections are likely to be somewhat decreased as compared with the case of the sharp and narrow peak. Okay, and this width of the peak is inversely related with the life of the excited state of the compound nucleus, right? अच्छा, एबे जो total cross section आमर आछी sigma t, and the radioactive capture cross section sigma of n gamma, they can be measured as the function of incident neutron energy. So some of the results are shown here in the figure, in which these cross sections are plotted as functions of energy in the intermediate range, that is from 10 to 500 kilo electron volt, and in this energy range total cross section ame ethi देखिया को पाउछु in case of your aluminum एठी. Okay, एही हिसाब रे तमरो peak टा आछि, right? Okay, so it has aluminum 27 pi, which is practically equal to the elastic scattering cross section, as only reactions in this case are elastic scattering and radioactive capture. Okay, it is y axis ra ame cross section nei jaichu in terms of barns, and this is our total cross section, right? Acha, tapre absorption cross section similarly y axis re milli barns nei gala absorption cross section एठी आछि, right? आ एठी देखिया को पाउछो in case of your aluminum for the case of neutrons, right? अच्छा, तापरे एबे जिबा resonance cross section आडको. Okay, देखो the reaction cross section sigma r for a particular entrance channel is obtained by summing over all possible resonance exit channel except of that of your elastic outgoing channel, that is alpha, such as sigma r equal to summation over beta sigma of alpha beta. Now if the elastic cross section sigma of xx suppose is included, then sigma total will be equal to kete reaction or elastic cross section ro summation. Simple. So actually elastic cross section comprises of two terms, duita term ethi rohuchi, gote hela compound elastic cross section a gote hela the shape elastic cross section. Okay, compound kono, it describes the probability of the compound elastic scattering and also called as the resonance scattering. Okay, so proceeding via an excited compound state. Our shape elastic kono, it is describing the probability of a state of elastic scattering. Also it is known as potential scattering, in which no appreciable penetration of the target or formation of compound nucleus occurs. So in terms of differential cross section for a scattering angle suppose theta, we can write the elastic cross section as the summation of the compound and the shape elastic with respect to angle, the scattering angle theta. Now the second term can be calculated directly from a given scattering potential obviously, while first को हमें directly calculate करि परिबा नहीं. But however total cross section, that is of compound and the shape, are calculated, or they are calculable from the modified form of Breit-Wigner formula. So Breit-Wigner formula को पुणी modify करा जाई परिबो, and it is possible to calculate the reaction cross section, that is sigma r, which is also measurable. So the quantity absorption cross section will be defined as sigma of absorption, which is equal to sigma r plus sigma compound elastic, and it is also calculable. We thus have the total cross section as sigma r plus sigma elastic, which is sigma absorb plus sigma shape elastic. Okay, this is measurable, this is calculable. तापर रोची elastic resonance scattering. Okay, मन रखो resonance केते बड़े हुए whenever there is two bodies having same state of vibration and they are brought close to each other. Okay, or same energy रोची same frequency रोची ताले संगे संगे amplitude से जगह रे ultimately पूरा high ही जाए. Okay, that is एटा मु कहली गोटे simple way रे basic way रे resonance रो definition टा. Okay, so elastic resonance scattering देखो ऊपर जो हमें देखिला equation 135, that can be applied to all resonance cross section except for the elastic re-emission of the incident particle like sigma xx, that is elastic resonance scattering. So besides compound nuclear scattering, that is when the absorption and re-emission of neutron is going on for the same energy, the incident particle wave is scattered by the nucleus as if it was an impenetrable sphere. So this type of scattering is known as potential or shape elastic scattering, and the elastic cross section sigma elastic is given by the modified Breit-Wigner formula, which is given as sigma elastic, which is 4 pi lambda cross square gc, then mod of gamma n by 2 e minus e0 plus I gamma by 2 plus e to the power I phi l sin phi l etiki rho whole square into plus 1 minus gc into sin square phi l. Eti phi l good factor aschi, which is an energy dependent quantity, a factor ta, and it is known as the hard sphere phase shift. Okay, at a phase shift the, and for the case l equal to 0, there is for the s wave neutrons we have phi equal to r by lambda cross, which is kr. So for the case of s wave neutrons on a spinless target, we have sigma elastic, एटा यहाँ reduce करिगला एतिकी value को. Okay, एठी हमें phi रो value put कर देला हिसाब रे. Hence here the coefficients 4 pi lambda cross square is maximum possible S wave scattering cross section, and the first term between the bars is called the resonance scattering amplitude, which if present along would lead to the equation 132 जोटा ऊपर हम ऑलरेडी देखि सारछु. किंतु सेकंड टर्म कोन एटा होची potential scattering amplitude, which if present alone will lead to the potential cross section, that is sigma shape elastic cross section for the neutron case, which is 4 pi lambda cross square sin square k r, right, because it is mod square achi. So this term varies smoothly with the energy, and for small value of energy as e tends to 0, we have k tends to 0 or kr is very less than 1. So sin kr को हमें nearly equal to kr लिखि परिबा, ताले shape elastic cross section reduce करिगला 4 pi r square को. So this is the potential scattering cross section for an impenetrable sphere when r is very less than lambda cross, and it is 4 times that of the geometrical cross section, which is pi r square. So the resonance terms rises to large energy values near e equal to e0, but is actually small elsewhere. Now for e less than e0, the two terms interfere destructively and it will yield a low value of sigma elastic, but for e greater than e0, the interference is constructive, and for the charged particles, resonance scattering involves the coherence between the Coulomb potential scattering, nuclear potential scattering, and the resonance scattering. Okay, finally we see the low energy neutron reaction. Okay, so for this purpose we will consider the lowest energy resonance of the compound nucleus, and for the case of E very less than E0, the denominator in the equation 136 does not change much with the energy E and gamma of gamma. Okay, and it is independent of E, but gamma n does depend upon E, and hence age of cross section for the neutron and gamma, it will be proportional to lambda square gamma n, right? So the probability of elastic emission of a neutron of energy E, which is having some momentum p, is proportional to the density of the states in momentum space around p, and hence gamma n will be proportional to p square dp by de. Kaiki emti hela? Because ame ei energy ku kinetic energy nouchu, which is p square by 2m. Hence de will be equal to p by m whole into dp. Tale we have sigma of n gamma proportional to lambda cross square p, right? So it is proportional to 1 by p, because lambda cross ro value kete h cross by p, eta tomar uncertainty relation ro asila. Tale 1 by p hela mane 1 by mv, m to chhado mass achi, so it is proportional to 1 by v. So it v egla velocity of neutron, and this equation is known as 1 by v law. So the Breit-Wigner formula leads to the conclusion that at low neutron energy, the cross section should be inversely proportional to the neutron speed or neutron velocity. And following 1 by v region, there occurs the resonance region, in which the cross section rises sharply to high value. So the cross section are low with neutron having very high energy. As you can see in this figure here, we have the emission of charged particles. Okay, as I said, this region is the 1 by v region. Tapare peak guda emti aschi, which are resonance peak. Then eta tolku jetobale aschi, we are going towards the fast neutrons. These are the slow neutron case. Okay, tale as I said, the emission of charged particles. So for the charged particles which are emitted in an exorgic neutron reaction, the low energy dependence of the cross section is dominated by 1 by Vn factor. Okay, yeah, upare depend karibo. But in case of endorgic reaction, the energy dependence near the threshold is dominated by the Coulomb penetration factor, which is gamma y equal to e to the power minus gamma, where the exponent gamma is equal to 1 by Vy. Okay, thus the cross section rises very slowly above the threshold value. And finally, for the charged particle induced reaction, all exorgic reactions at low energy are dominated by the Coulomb penetration factor of the incident particle. And in case of your endorgic reaction, they have an energy dependence near the threshold of the form as given above. Okay, so एठी ग्राफ को आमे नीचु क्रॉस सेक्शन नेगला y axis रे neutron energy in terms of electron volt नेगला x axis रे. We are getting such type of a graph. Okay, so this is all about the resonance and the Breit-Wigner dispersion formula, which I have taken from one book. Now this is what I have taken from another book also. एठी भी या विषय रे explain करिछि. So एई बही रो भी तमे पढी पारो. Okay, and एठी देखो सेम जिनस प्राय सेम ही अच्छी. ओके, दुईटा जाक बुक रे. फाइनली देखो आमे जाऊचु पार्टिकल विथ स्पिन. जेतबेले स्पिन कंसीडर करछि, जी फैक्टर आसला, देन न्यूट्रॉन रिजोनेंसेस एट लो एनर्जी, इंटरफेरेंस आसुची, पोटेंशियल जो आसची आउ तमरो कंपाउंड रो. ओके, सो ई हिसाब रे तमे एई बही रो भी एज आई सेड यू कैन रीड एंड मेक योर नोट अकॉर्डिंगली. एठी देखो रिजोनेंस पीक गुडा आसची, राइट? चार्ज पार्टिकल रिजोनेंसेस. ओके, এটা আসছে দেখো রিজোনেন্স পিকটা, রাইট? সো এই বহিরু भी তুমি পড়ি পারো and make your note accordingly as brief as possible. Okay,
thank you.